I'm going to give you a general picture about this class, this statics, and then I'll come back to go through each chapter, okay? And if you have any questions, feel free to let me know anytime. So let me grab my pen. Okay, so I'm going to just draw a kind of diagram. So the key part in this class, of course, is called the statics. Can you see here? Okay, so the key part of this class static is chapter 4, in fact, because all the fundamental principles are from chapter 4. And then the question is, what is chapter 4 talking about, right? Chapter 4 talk about the equilibrium conditions, or equilibrium equations, or equilibrium state for a rigid body. So basically, we're talking about equilibrium of two-dimensional or three-dimensional rigid bodies. And then, of course, you need to know, if we're talking about two-dimensional rigid body, we should have three independent equations, okay, to solve for three unknowns. So that is basically the fundamental thing, actually, for the whole class. Okay, so for any two-dimensional rigid body problems, if you plot the free body diagram, you should end up with the three equations. Okay? And then if we're talking about three-dimensional rigid body problems, then actually you should have 6 equations for three-dimensional. Okay? We talk about both. The other question you may ask is, when I gave you those equations, when I gave you those questions for you to answer, I'm expecting you for any test, or we already have we have done with the 2 midterm. Now we're just kind of having the finals, right? When I give you an equation, when I give you a question, I'm asking you to solve for something, but it doesn't mean I just want you to write down that something directly. I'm asking you to show the work, the procedures, to finally end up with your solution. And of course, hopefully you highlight, you box those solutions. But I don't want to see that box only. If I see that only box giving the numbers saying force equal to something in a certain direction, period, basically I don't trust much about what you're trying to solve, because you don't show me how you solve the problem. And I really want to see the procedures you are trying to solve the problem. Many students may not like to plot or draw the free body diagram. That's really not good. Let me tell you, if you can use a very simple way or ignore something, but no matter what, you show the work, if I try my best, the grader tries their best to understand, you finally get the correct answers, most likely you won't lose credit. But if you are not drawing, or if you are not drawing at all, if you draw a lousy free body diagram, and then your answers are not correct, we have to heavily penalize you. Because number one, you didn't get a correct answer. Number two, we assume you don't know how to draw the free body diagram. Okay? So if you can draw a free body diagram in a very nice way, neat way, and we saw which is good, and your final answer for whatever reason is not correct, then we assume, or we can reasonably follow your procedures, and we find out the reason you get a wrong answer is because numerical mistake. Because sometimes you might have a chance to make mistakes by punching the different number. If that's the case, you receive very less penalty, because we understand physically you are doing nothing wrong, but for whatever reason you didn't punch your calculator correctly. But if you do not tell us the story, you're trying to solve the problem, and you did not draw the free body diagram correctly, then there's no consistency. Okay, so for example, you didn't draw forces, and then when you write those 3 equations, I saw all those forces, then how can I assume you understand the problem? Because what you're writing is not consistent with what you're plotting. Then you may say, well, I don't want to plot anything. If that's the case, if you can write down those equations very nicely, all correct, that's probably no problem. But if you are not writing those equations correctly and you could not get a correct answer, then we have to assume you don't understand how to solve the problem by first going into the free body diagram drawing. The bottom line is, I want to see the details about the procedures for solving the problem. Of course, I would like to see your final answer. But if you only want to write the final answer without giving us the details, we cannot assume the way you are trying to solve is correct. So that's why I keep telling you it's important to show the work. I'm not asking you any concept questions. I'm always giving you those real kind of problem-solving questions. And I would like to see the procedure you're trying to solve. Okay? So for whatever reason, if you believe you did something wrong, you need to cross out those. Some students gave me multiple answers. Okay, so on this left side for this problem, they solve it. And for whatever reason, they thought, well, this may not be correct. And then continue to start on the right side to resolve the problem. And give me two answers. How can I decide which one is right? You need to decide. If you believe the right side is correct, then cross out the left side. If you believe the left side is correct, then cross out the right side. If you ask us to decide, we're going to decide the bad one for you. Okay? So do not assume we're going to collect the correct answer for you. It's not our responsibility. If that's the case, we can solve everything for you. We don't need you to take the test. Okay? Because we are testing you, in fact. Okay? So try to understand there's really nothing wrong, but if you believe there's something not correct, you need to cross off that or erase those. Don't leave any confusions. If you let us decide, most likely we're not going to decide on your side. Okay? So back to this one, chapter 4, which is the most important part, talking about the free body diagrams and establishing those 3 equations for 2-dimensional rigid body problems or 6 equations for 3-dimensional rigid body problems. So that's the key in this class. Then there's a special case related with this one. That's in chapter 2. So I'm going to plot chapter 2 a little bit smaller because that's the special case, which is talk about the equilibrium conditions for a single particle. So if we talk about the equilibrium condition for a single particle, that is one material point, then you will have 2 equations for 2-dimensional problems or 3 equations for 3-dimensional problems. Okay, so that's the special case of this. And all the other chapters are pretty much serving for this purpose. Okay, so for example, this is chapter 2, we did it. What is chapter 3? Chapter 3 is a preparation for this chapter 4, which is called the moment and force couple systems. So this part, chapter 3, does not talk about equilibrium condition at all. Okay, so this part basically talk about the moment and the force couple system, which is the preparation for chapter 4. Because those governing equations we obtain are based on chapter 3. Because one of the equations for 2-dimensional problem in chapter 4 is to establish a moment equation. So without chapter 3, there's no way you can establish the moment equation. So that's why that chapter 3 is the preparation for chapter 4. But once we are done with chapter 2, chapter 3, chapter 4, I forgot this is chapter 3, right? Then we are going to have some kind of applications. Okay, just use the fundamental principles to solve specific problems. The first specific problem is chapter 6, talk about truss problems. Okay, so truss problems. We are basically, as a first step, we need to calculate reactions. So that's exactly chapter 4. But after we got all the reactions for the given 2-dimensional truss structure, then our next job is to calculate the internal forces. Okay, so which I'm going to go over those a little bit later on. So this is the one special case. And we do talk about another special case, which is called beam problems, which is chapter 7. We talk about shear and moment diagrams. Okay, and this is also very important. In chapter 6, when we talk about internal forces in trusses, those forces are constant. But of course, you do need to identify it is in tension or it's in compression. But in general, that's a constant. But when we later move to chapter 7, the shear force, which is internal force, and the bending moment, which are not internal force, are no longer constant. And then you have to plot a diagram. And that's called the shear diagram and the moment diagram. Again, do not, I'm going to only get, of course, there's at least one question for the chapter 7, no doubt about it, right? I'm going to only ask you plot or determine the shear and moment diagrams. This is, of course, a question, but do not just plot directly. Okay, so if you do not show the procedure, just plot the final answer directly, there's no way we can correctly evaluate what you did in terms of the procedures. So you do need to show the details. Okay, and then we talk about another two cases, which is a chapter 5 first, which is called the centroid. The reason we talk about centroid is because this centroid is the same concept which we call the center of gravity. So center of gravity is the physical concept. In order for us to make an equivalent assumption, when you have a distributed load, which is equivalent to a concentrated load acting on somewhere, that somewhere is called a centroid. And basically we use the same concept we learned from chapter 3 by talking about the single force system. Okay? And now we finally talk about chapter 9, which is called the moment of inertia. And this is another special case. Instead of talking about the centroid, this time we talk about how rigid the beam is by evaluating that kind of specific parameter we call I. And physically, that I is called the moment of inertia. Okay? So this is basically the whole thing we have introduced in this class. Of course, you may say, how about cables? I did spend just a little bit of time talking about cables, which is part of chapter 7. And I did spend a little bit of time talk about what's called the friction, specifically called the belt friction. That is part of chapter 8. But these two parts will not be covered in the final exam because I even did not give you any homework, right? So you don't need to worry about this. But I did briefly talk about, I just gave you some kind of introduction about those specific structures. One is called the cable, and if they have a belt friction, how you are going to calculate those friction forces. But these two parts will not be covered in the final exam. Okay, and I didn't give you any homework questions either. So this is the general picture. Now what I'm going to do is to switch back to the my lecture notes to talk about what we have learned chapter by chapter. Any questions so far? Okay, chapter 1 is kind of a concept. There's no question from chapter 1, of course, okay? But there's one thing I do want you to pay attention, which is my last slide. That is called the numerical accuracy we need to follow typically. That is what we call the last part, numerical accuracy. But since I just used this my slide, I'm going to tell you now, most likely you are going to take dynamics with either CEEMAE30 or MAE30, right, next quarter, because we offer that one. And then most likely when you are entering junior year, you're going to take this class, which is called CE150 or MAE150, I believe. A certain amount of students most likely will take the mechanics of fluid as well. In civil engineering, that is 170, I believe, but in mechanical, I forgot the number. It's probably 151 or something else. Okay, I just want to mention one thing in the last slides. Two things in the last slides. This is one thing I want to mention, okay? So when you have a final answer, if the first digit is any number other than 1, you need to keep 3 digits, okay? So that's the typical. It doesn't mean we have to penalize you if just in case you write a lot of digits, but you should train yourself to have a good habit when you write those numbers. Okay, so this is a kind of widely accepted in engineering community. If the first digit is 1, then you need to finally keep with a 4 digit for your solution, okay? The other thing I want to mention is this. For some questions, we'll be using international system units, right? If that's the case, whenever we talk about self-weight, okay, typically we gave you the self-weight in terms of gram, the kilogram. So you need to multiply with 9.81 to transfer kilogram into Newton, because kilogram is not the unit for force. Okay, it's a unit for mass. If you want to treat the self-weight as a force, then you need to multiply with 9.81. But for U.S. system, you don't need to, because the U.S. system, the self-weight is in terms of pound, and pound itself is the unit for the force. So that's why you don't need to. That's only for international unit. Okay, so there will be no questions from chapter 1 directly, but these are the concepts you'll probably need to implement into any questions you are asked to solve. Okay? Any questions? Chapter 1? So sometimes if you are sitting on the rear side, just talk directly, because I really cannot see whether you raise your hands or not. Okay, so chapter 2, which is a special case of chapter 4, as we can see right now, is talking about statics of particles, or say equilibrium condition of a given particle. Particle means, in this chapter, means it's a single point with no geometry, with no size. So that's why we call the special case of the rigid body. But of course, we are splitting the static of particles into two-dimensional and the three-dimensional problems. No matter what, for two-dimensional problems, we need to know how to decompose any force into x and y components, okay? Especially when you have a multiple forces acting on the same point, the best way to solve the problem is to use a component method. And actually, pretty much all example I talk about, no matter which chapter, I always use the component method, if you recall what I have taught so far, right? I never use what is called the law of sine, law of cosine. I did mention briefly here at that time, law of cosine, law of sine, but actually I never use. Which means you don't have to use this method to solve. But on the other hand, if you say, I'm so good on this method of, I'm so good on geometry, the trigonometry method by taking advantage of law of cosines, law of sine, there's really nothing wrong. Okay? As long as you show the detailed procedures, we will give you credit if you do correctly. Okay? I'm not forcing you to use component method, but I myself prefer to use a component method to solve any problem in this class, because I believe this method can solve really 100% problem. And it is very straightforward. Sometimes it takes a little bit more time, just probably 5 more minutes. But you can pretty much get the correct answer. Okay? So now, how to calculate the components of a given force. Obviously, the force is a vector. You just split it into two components, x and y, and you can calculate the components based on the magnitude and the angle. Talking about this one, sometimes when during the test, students may ask a question like this. Oh, you asked me to calculate the force. Do I need to give you the magnitude of the force and the direction, or I just gave you the component? Well, what do you do when you are dealing with the homework questions? If I basically ask you, calculate the force, you can give me either way. If you like to give me the magnitude and the direction, no problem. If you want to give me the two components, then no problem either. So I don't think it's a good idea you ask me such a question. Because if you ask me the question, then I even do not know how to answer. If I say, okay, calculate the magnitude, then some other students say, well, I don't want to calculate the magnitude. You did not ask me. Why do I have to? Right? So unless I ask you specifically calculate the magnitude, then of course you have to do. Otherwise you don't have to. You can calculate the magnitude and the direction, fine, or you can just give me the two components. That's perfectly correct. Okay, so it's always consistent with those homework questions. So that's why sometimes I said, do not ask me any technical questions. If the problem itself is designed wrong, then I'm responsible. Okay, so you can complain to anything, to any extent you like, if the question itself is wrong. But if the question is well designed, and for whatever reason you may be confused, you need to try your best to recall what you did for those similar questions when you were handling those homework questions. Because otherwise, it may not be fair. If I say, okay, calculate the magnitude, and then the neighbor is busy writing something, oh, then I have to calculate the magnitude, but actually it may not be required. Okay, so just look at the description more carefully. You should be able to figure out what's the question we're really asking you. Okay, again, I never ask you very strange questions. Okay, the component method is especially useful when we have multiple forces acting on the same point. But the bottom line is, once you have all the forces acting at the same point, then you need to decompose all the forces into x and y directions. You add all x component forces together equal to 0, and add all y component forces equal to 0 to solve for two unknowns. And these are the typical two equations we use for solving any two-dimensional particle equilibrium problems. Okay, and this is what we call, this is the first time we introduced the free body diagram. Okay, no matter you like it or not, this is the basis. In fact, I'm keep telling you, these equations are not established based on this. Okay, this is not called the free body diagram. This is called the free body diagram. Those equations are established based on the free body diagram. Okay, so that's why I believe it's very important you need to know how to plot the free body diagram. Once you plot the free body diagram, then we know you're basically dealing with 3 forces or 4 forces or whatever, and then we check your equations to make sure those equations are correct. Even though your final answer may be wrong, that's just because of numerical mistake. If that's the case, you just get very less penalty. But if you do not draw this one, and then you did not write those correctly, then you get a lot of penalty, because we even don't know whether you can draw this free body diagram correctly, because we cannot make any assumptions if you do not say anything. Okay? So that is the first part in chapter 2. And then the second part in chapter 2 is to talk about three-dimensional cases. So this part is important because the previous part in chapter 2 are really simple. It's kind of part of the special cases of college physics when we talk about mechanics problem. But for three-dimensional force vector, how are we going to calculate the three components? I believe that's very important, especially this is the equation we have to use frequently in chapter 3, chapter 4 later, right? And that's the equation to describe a force vector in three-dimensional setting. It's always equal to the magnitude of the force multiplied with the unit vector. Okay? So the left-hand side of the equation is 100% physical concept. But now you are splitting a completely physical concept into physics and the mathematics, because the magnitude is physics, but lambda is in fact a mathematics, because that's called the unit vector. It has nothing to do with the force. It just basically calculated, evaluated based on the 2 points you can find, and then you can calculate lambda. So now the question, how are we going to calculate lambda? The lambda calculation is to follow this procedure, right? So basically, you just randomly pick 2 points, but you do need to know the force direction, by the way. Okay? So by now, I don't think you have any problem to indicate the direction of the force. Once you know the force is directed through this way, typically, you need to find 2 points, use end point, subtract the start point. Okay? So that means n subtract m. You have 3 components of m, you have 3 components of n, you use n subtract m, and don't forget to divide it by the distance between m and n, so that you can finally get this lambda. And that is what we call the unit vector. Once we get a unit vector, then we can describe a three-dimensional force vector in terms of this equation. Sometimes, occasionally, we are asking you to calculate the direction cosines of this three-dimensional force vector, which means you do need to calculate these 3 angles, theta x, theta y, theta z. And these are the direction cosines. In other words, they are determining the direction of the force. So again, if we ask you to calculate a three-dimensional force vector, do you need to calculate the magnitude and direction or not? If we do not ask you, you don't have to. Okay? If we ask you to calculate the magnitude and the direction of the three-dimensional force, then obviously you do need to calculate those 3 angles. And that's the only way to describe the three-dimensional force direction. Okay? But many times we do not ask you. If we do not ask you, typically you just calculate those 3 components. This is called fx, this is called fy, and this is called fc. So you just write that three-dimensional force in terms of I something times I plus something times j plus something times k. That's it. Okay? Any questions? Okay. The reason I'm saying this for three-dimensional force vector, that's equation, let me give you back again, this one, because this equation is not only used in this chapter, it will be continued use in chapter 3 and chapter 4, right? So that's why every time we have to deal with this three-dimensional force vector. Any questions? Okay, now we are moving to the next chapter, chapter 3. Chapter 3 talk about two things. Number one, we call the moment concept, which is kind of part of the generalized force, but we just gave a name called the moment. And sometimes you want to call it torque, there's no problem. But typically we call it moment in this book. And the second part is what we call the equilibrium system of forces, or in other words, we call the equilibrium force coupled systems. Okay, so we're going to go over both of them. So the first part, we talk about moments. There's three kinds of moments. The first kind of moment is called the moment of a force about the given point. And so we end up with a moment vector. And this concept has been used until chapter 7. You know, in chapter 7, we also talk about this, right? So what is a moment of a force about a given point? So we keep using that. The second part, the second kind of moment is called a moment of a force about a given axis. This is not widely used, in fact, right? But somehow you do need to know because this is a projection of the first type of moment. Okay, it's a projection. If it's a projection, that means it's just a scalar. It's no longer a vector. But the first type of moment, a moment of force about a point, is called a vector. In other words, for three-dimensional problem, you really have to use ijk to represent. For two-dimensional problem, you can either use I and j, or you use a clockwise, counterclockwise to represent. The third kind of moment is called a moment due to a couple. This is not the real kind of physically existing moment. It is a virtual thing, but helping us to move forces from one point to another point. And that's why we're also talking about the third type of moment called a moment due to a couple. So let's quickly go through these three kind of moments. The first one is a moment of a force about a given point. So for any three-dimensional problem, when you have a force acting on anywhere inside on the surface of a rigid body, once we know this force, if we were asked to calculate the moment of this force about any other point, point O for example, so then this is what we call the moment of force about a point. So typically, by definition, is R cross F. And that's a very important equation because for any three-dimensional problem, where's that equation? This one, right? So for any three-dimensional problem, typically this is the only equation you have to use to calculate the moment of a force about a given point. That's probably the only equation because I don't think I talk about any other equation to calculate a three-dimensional case moment, right? So that's the only equation. So that's why you just have to start from this equation. And then you're going to think about how I'm going to evaluate this R and how I'm going to evaluate this force. So if we give you a simple problem, calculating a moment of a force vector about a point, just in case you have nothing you can do, if you write this equation, then at least we say, well, you know at least 10 or 20% of the question, right? If you only have 1 minute, for example, to submit your work, you can write this equation. I don't think you get 0 point. You get some points. Of course, next one, when you have more time, you can evaluate how to get R and how to get F, and then you use the cross product. And that's what I call procedures. So if I have no idea how to calculate this one, that means you don't know how to write the final answer. But if you can start from here, then at least we know you know something. Okay, so write more, make more sense, in fact. Okay, so this is the first kind of moment to calculate three-dimensional force at a certain point. And then what is R? R is the distance vector. This is a vector, right? Distance vector from the point you want to calculate the moment on to the point the force applied. So that's it for this one. This R is from O to A. If from O to A, then you're going to use A subtract O. Okay, so each person can have a different way to evaluate. The bottom line is this R is the vector using three components A subtracts three components of O. I'm not forcing you. You have to follow exactly what I keep saying. You need to find your own way. But if your way is not correct, then of course you cannot get a correct answer. Especially if you evaluate this R in the wrong way, I assume you don't know the physics. So don't complain by that time, say, oh, that's the numerical mistake. There's not a numerical mistake if you cannot calculate this R correctly. Because I keep saying from O to A, that means use A subtract O, and that's called the distance vector. And then the force vector is to use the concept we just talked about in chapter 2, right? So basically this force equal to magnitude of the force multiplied with the lambda. I probably have somewhere. Okay, anyway, so if we go back to look at chapter 2, right?